So the topic of my today's presentation of the second week of the microwave remote sensing in hydrology. I'm starting. Topic I'll cover is scattering of microwaves. Atmospheric scattering occurs when particles or gaseous molecules present in the atmosphere cause the electromagnetic waves to be redirected from their original path. The amount of scattering depends on several factors, includes wavelength of the radiation, amount of particles and gases present in the atmosphere, and the distance traveled by the radiation through the atmosphere. In the visible wavelengths, 100% in case of cloud cover to 5% in case of a clear atmosphere of the energy received by the sensor is directly contributed by the atmosphere. So there are three types of scattering: Rayleigh, Mie, and non-selective. Rayleigh scattering, where the particles are smaller than the wavelength of the incoming light or our signal. Examples like tiny speckles of dust, nitrogen, oxygen molecules, these. So the effect of Rayleigh scattering is inversely proportional to the wavelength. That is, the shorter the wavelengths are scattered more than the longer wavelengths. So shorter the wavelengths, it will scatter more. In the absence of particles and scattering, the sky would appear black. That's why our sky looks blue. Daytime, the sun rays travel the shortest distance through the atmosphere. In that situation, Rayleigh scattering causes a clear sky to be observed as blue because this is the shortest wavelength the human eye can observe. So at sunrise and sunset, however, the sun rays travel a longer distance through the Earth's atmosphere before they reach the surface. All the shorter wavelengths are scattered after some distance, and only the longer wavelengths reach the Earth's surface, and as a result, the sky appears orange or red. In the context of satellite remote sensing, Rayleigh scattering is the most important type of scattering. In general, the Rayleigh scattering diminishes the contrast in photos, thus has a negative effect on the possibilities for interpretation. When dealing with digital data, as provided by scanners, the distortion of the spectral characteristics of the surface may limit the possibilities for image classification. Next is Mie scattering. Mie scattering occurs when the wavelength of the incoming radiation is similar in size to that of the atmospheric particle. That is, the wavelength of the signal is similar size of the atmospheric particles or the particles it is going through. Mie scattering is caused by aerosols, which are mixture of gases, water vapor and dust. In our case, this can be the rain clouds, like that. So it is generally restricted to the lower atmosphere where larger particles are more abundant and dominates under overcast cloud conditions. Mie scattering influences the entire spectral region from the near ultraviolet including a near infrared. Third one is non-selective scattering. Non-selective occurs when the particle size is much larger than the radiation wavelength. So typical particles responsible for this effect are water droplets and larger dust particles. And non-selective scattering is independent of wavelength. That's why it is not for use for our purpose. So finally scattering. Finally, what when a signal, or an energy is incident on any given feature of Earth's surface, three fundamental phenomena happens. It's either gets reflected, gets absorbed, and gets transmitted. So we are interested in these three phenomena. That is the transmission, the reflection, and the absorption. Why we are interested in case of radar? So what happens? This is the proportions of energy reflected, absorbed and transmitted vary for different earth features and depend on the material type and condition of the feature. Variations permit to distinguish different features appearing on an image. So every target has different capacity to reflect the energy, to absorb, to transmit. But for our type of our domain, that is the radar or microwave. For microwave domain, what is, I mean, it is not like every sensor captures everything, right? Reflection or emission, absorption, like that. Microwave sensor captures only the reflected energy. So why the scattering comes? The scattered energy. So scattered energy also, or scattered signal, it is also, it comes under reflected energy. But why we are more interested in scattering, and also in future we will use the term backscatter. Why to use the backscatter? Because reflection, like, it is after all a reflected energy, it is reflecting. Scattering, it is, suppose it is one signal is getting transmitted, getting reflected, and when it hits the target and gets reflects in every direction, so it is called scattered. But why backscatter? So the radar sensor, it captures only that part of the signal, reflected signal, that that is directed towards the sensor. That is, once there is one sensor, it transmits one signal, and the signal gets reflected to all direction, but only it takes that reflected signal only that is directed towards the sensor only, not that is going anywhere else direction. That is called the backscatter signal. That is, it is taking only that portion of the scattered signal that is back directional or backwards to the sensor. So to understand radar, how, particularly what, which signal or which energy it captures or it senses from a target, it is very important. It does it sense the emission or emitted energy? No. Does it sense the reflected or scattered? No. Not reflected energy is not the correct one to answer, because reflection happens, normally we call it is only one directional. But radar, if it, that direction is towards sensor, then it is okay. But radar, I mean, transmits the signal, and that type of signal, that the way that it gets scattered to all everywhere, and get the signal that is directed towards the sensor. So we will call every signal, everything, as a backscatter. The phenomena happens backscattering when the signal hits, in terms of microwave, in terms of radar, the signal that hits, and we get the backscattering signal, backscattered signal. Yes. Like that diffuse, like specular reflection, that is the reflected energy that is only getting transmitted, hitting the target, and one way. But for this type of surface, like this, that is mostly natural. Here also it is showing that this this specular reflection, but in reality, everywhere depends on the wavelength, depends on the that frequency, also sensor, that diffuse scattering happens. So suppose it is transmitted, the signal is transmitted, hitting here, and it reflects the energy or scatters the energy in all the direction, but sensor is here, so it will we'll call this signal as backscatter signal, which is directional to this, and this signal only the radar captures or receives. Not, it is not interested to these signals, or it cannot capture these other way directional signals. Now I also, the effect of different atmospheric this presence on the microwave, I covered this previous also, how it affects, or the microwave, how it differs. for ice clouds, for water clouds. This centimeter, this scale is important and better to go so on, because our sensor starts from, suppose from say 3 centimeter, like the X band or Terasar X satellite, from 3 centimeter. So it gets, I mean, it can penetrate this much and so on. So normally more than 4 centimeter it can penetrate, or it can not, we will get the cloud free signal. For rain also similar, these graphs I will not cover that much. For this is important for like soil moisture and this depth, and according to these bands, why particular these bands 3 centimeter, 7.5 centimeter and 23 centimeters, because these are the bands we mostly work with and we get data also. Like starting from 3 centimeter, if lower, it will not penetrate that much. So you can see in here it start when the soil moisture is, I mean, it is totally dry, you can say the grains are not holding any moisture, and it decreases as it, I mean, the soil moisture increases. So that counts for 3 centimeter wavelength, that is the X band, and one satellite can be Terasar X, another can be Cosmos Skymet. So these satellites are very useful to know, to get to know the sensors and to know the band, the particular bands they are used. Second is the 7.5 centimeter. It is one, it can be C band. Like it starts from approx 6 to 7.5 centimeter. So how C band works? It lies between the, I mean, X band is here, then the medium level. It is the C band, and this 23 centimeter, 23 point something centimeter, it is it is L band, that we, I think in future we will work with allos 2 data, that is L band data, and that has this wavelength, this 23 centimeter. It is considered as larger wavelength than these one, and it gets penetrated to centimeter level to our ground earth, and that depends on the soil moisture also. Similarly, I showed this, also discussed this in the first week. So how the different wavelength, their moisture content and density of vegetation also, and incidence angle, it, I mean, differs from different wavelength sensors. These images are very useful. Now it seems like not so much, but later on when working with different projects, so this type of crops, how it is reacting, and this any type of trees, if there is crops it will react one way, if trees it will react another way, so like that. Now we will start the radar, or better call say, I mean, say, synthetic aperture radar. We'll start from very basics, and there are very details to understand. So radar, the full form is radio detection and ranging. That is, a radar operates by radiating electromagnetic energy and detecting the echo returned from reflecting objects or targets. So nature of the echo signal provides information about the target. And the range or distance, the terms are very important. The range to the target is found from the time it takes for the radiated energy to travel to the target and back. The angular location of the target is found with a directive antenna with narrow beam width to sense the angle of arrival of the echo signal. If the target is moving, a radar can derive its track or trajectory and predict the future location. The shift in frequency of the received echo due to the Doppler effect caused by moving target allows a radar to separate desired moving targets, such as aircraft. This, even though the stationary echo signal may be many orders of magnitude greater than the moving target. So basically, so many lines. But to understand from this slide is, what is radar? It is sending one electromagnetic energy, one chirp, pulse, or better called chirp. So it is sending or transmitting one chirp to one direction, and hitting one target, suppose one piece of land, and it is taking back the reflected signal. That's it. And this is the way it will take get or it will capture the or store the received signal, and it will analyze. That is the what the radar it does. And what is the these terms coming, the time it takes for radiated energy. So all these things it is doing to measure some distance, that ultimately the distance it will calculate, that is the range or the distance, that the time it takes for the radiated energy to travel to the target and back. That is it, how much it is taking. So it will take the double the time. Suppose how much it is taking to going to hitting the to hit the target and coming back. So the distance it is same distance it is covering. So that there we'll see this in detail. That part we are interesting, we get some type of distance here. And one thing to understand also, to know that this microwave energy or signal, it travels in the speed of light. So we will use the speed of light, that is 3 into 10 to the power 8 meter per second, that that as our uh, the speed of the signal. And there is another phenomena that happens. So how radar started, I told you, during World War II, and for the security and surveillance purpose mainly. So that time they for tracking, for detecting, I mean opposition, their any kind of vehicle, their movement, this kind of, for this purpose the radar it started. So there they use the Doppler effect, or it came. Suppose one target is moving. For our purpose, it is stationary or it is not moving. But for like how it started, when we want to, I mean, detect one moving car. So there the Doppler effect, like how it is going, when it is going far, the sound it creates. So similarly, this not here for the sound, here the microwave the signal. So it gets, I mean, very, I mean it gets decreasing, and when also coming nearer it gets increasing. So that's the Doppler effect, and that has very role for radar. Now this is how this image is very important to understand how actually the wave interacts or hits, to understand basic. Like suppose these are different targets and this is the sensor, you can say some sensor is there and this is the aircraft moving. So it sends these solid lines. So if you number the suppose waves or signals, so 1 2 3 4 and so on, it is hitting and it is getting back the signal like the this way, like the 9 number is here, so 9 it is getting back like that, because we'll see how it moves, then we can. So the return signal that hits the number 8, suppose return signal is here, so it is not, I mean, exactly spaced like the wave. Suppose I think wave suppose is here like the sinusoidal waves like this, and the receiving wave will not be like the matching one. So to understand here, that in the wave we will get the target's impression like this, return from the house will be different for the transmitted signal, it is the return signal. and it has some peak. In the transmitted signal it will be the same, and return signal there is peak. So we detect the targets, or we sense the target. Okay, here some targets. So the cross range resolution, what to say, the cross range, that is the radar is moving, it's that is not parallel, or that is perpendicular to its moving path, that is called cross range. We'll see in geometry. Resolution of a synthetic aperture radar SAR for imaging a scene such as terrain can be explained as being due to resolution in Doppler, although a SAR is usually thought of as generating a large synthetic antenna by storing received signal in a memory. So the two views, that is Doppler resolution and synthetic antenna, are equivalent. So finally, radar is an active device in that it carries its own transmitter and does not depend on ambient radiation. Depends on the reflected or scattered signal. Ambient radiation that the optical and infrared sensors do, that depends. So radar can detect relatively small targets at near or far distance and can measure their range with precision in all weather. So all over radar, what these terms are coming, the synthetic antenna or SAR, synthetic aperture radar, synthetic antenna. What does it mean by synthetic? And also the Doppler resolution, synthetic antenna, these cross range resolution. So we'll look after. This slide I put just to give you, normally in remote sensing and in this type of application oriented talks, we don't, or we skip these things, but it is better to know at least something about. So the radar, actually we are interested more on the how signal is, signal is interacting with the targets and this signal processing after. But the sensor which transmits the signal and which receives the signal, we need to know something about that, that what is actually happening, what it is doing with the wave. Okay, wave signal. So this is the basic diagram of a radar that consists an antenna. So the antenna, then these terms come: the duplexer, power amplifier, waveform generator, and duplexer is connected with low noise amplifier, local oscillator, mixture, then IF amplifier, matched filter. This is very important, matched filter. Second detector, BD amplifier. So this is simplified, this is the basic one. So this, every block has its own task, its own, for generating and for receiving and also processing the initial radar signal. We will process, or we get the data after this. It is not like we only process, the sensor itself process something. So you can go through this, that what the duplexer does, what a return echo signal, it is collected by antenna, amplified by receiver. So normally, I mean, the signal, what the power amplifier does, it amplifies. From the name we can understand, it amplifies the signal, you can say. And also there is one term, signal to noise ratio. Basically it amplifies that part, so that it gets, we will not lose anything from noise or clutter. Okay, we will amplify the signal. And matched filter, as I shown you in this, suppose if we consider this, how a wave is reacting. So one wave is suppose going, I will try to show again. Suppose one wave is going transmitted. and another wave. This is the transmitted signal. Then the received signal will have some phase shift, that is it will be shifted to, because in that time the sensor moved, so it will be shifted a little bit. So received signal will be somewhere like that, it will not match. Okay, and it will have different peaks and different types, both are not same, and it will be shifted this direction. So what match filter does, it, like, after all we have to detect how the reflected, the reflected signal has some property of hitting the target. It gets changed, but where, and where it gets changed, to detect that or to understand that, in layman language, match filter does, suppose it creates one transmitted energy, it takes the form of the transmitted energy, and it overlaps, it match the receive, it match this with, then it finds that where are the peaks or where are the changes. So this is how to understand actually what is happening. It is very important. That is what the match filter does. Then also the display and so many things, mixture, this all has its own task. So basically the radar. Now we will see some diagrams and understand actually how it moves and what are terms different. So there is one antenna. It is suppose our land or foot earth surface that we are supposed to illuminate or detect something, and it transmits energy, this one bundle of energy. Okay, so the footprints are like that, it is not like one point, it has one area, and the area, it looks like it has some nearby point and the furthest point, like that. So now comes the very important slide. So the radar equation, to understand it through equation, if you see the equation here, it is called the, all are taken from this book, I will share the link. So it is the reflected power. Okay, we'll work with power, that I will also discuss after some time. So this is the received power, PR is equal to PT, transmitted power, GT, that is G is the antenna gain, it is called, by 4 pi r square. This r is called range, the range we are interested, or the distance we are interested to measure, into sigma is radar cross section, that is the target it is hitting, that cross section, by again 4 pi r square into A, that is the area. So here it is the same thing is written, is a power density, distance r, it is called also power density, meters from a radar, radius a power of P, watts from an antenna of gain G, numerator, all are here. And one thing to understand from this equation is, which, like, there is numerator, denominator. So if we want to increase our r, this distance, what to do, that is, first we have to understand which are constant. Constant is G, this gain, it is like antenna factor, how much efficient the antenna. Okay, and ideal antenna has gain 1, gain is equal to 1, that is not real. So in that term, how much directional one antenna can send the signal. So the more the better, the more it is directional and dense signal, more the gain. It depends totally on antenna, and it is a constant. Sigma also, it is radar cross section, and it is the also effective aperture area, and 4 pi these are constant. So basically this received power, it depends universally, proportional to r square, or better called r to the power 4, that is the r. So we can visualize, if we want to increase r, we have to decrease the received signal, or we want to numerically we want to decrease r, that is, so we have to increase the receive signal. To increase the receive signal, what to first thing what we have to do, we have to increase the transmitted signal also. So that way we have to visualize these radar equation. There comes one, the signal to noise ratio also. So the minimum detectable signal, that is S min, which appears in the radar equation, is a statistical quantity and must be described in terms of the probability of detection and the probability of a false alarm. So this is very important, can be expressed as the signal to noise ratio. And also this we call it like minimum detectable signal is KTBF, the signal to noise ratio. These are the constant K, T, B is bandwidth, and F is some noise, Fn is noise. So this is the minimum detectable signal that is required. So as we were seeing that, I was telling that to maximize the range, what we have to do, it runs with 1/4 power of the, that is inversely proportional, 1/4 power of all these. But better or further, what we have to focus, some are constant and some are which we can manually change, or we can change. So what we can change here, as I said, it is r to the this gain and radar cross section lambda, these all are constant for a particular sensor or antenna. So but this received and this transmitted, these is the this or increases or decreases the range with the 1/4 power of the this. So we are interested in maximum range equation. Now comes the radar cross section. It is also very important because we are interested in detecting target, for detecting and measuring target also. For these those who works with this moving radar and moving vehicle too, they are more interested in just detecting the target, no measurement, or the target safe is, it doesn't matter that much for them. They want, for security purpose, they want to just detect the moving vehicle in periphery. But for us, we have something to do with the cross section or area of the target. So radar detects or tracks a target and sometimes can identify it only because there is an echo signal. It is therefore critical in the design and operation of radars to be able to quantify or otherwise describe the echo, especially in terms of such target characteristics as size, shape and orientation. For that purpose, the target is described as effective area called the radar cross section. So effective area, it is the projected area of a metal sphere which would return the same echo signal as the target had the sphere been substituted for the target. So you can see we already studied different types of this scattering, this region, and how these, with increasing of the radar cross section of suppose one sphere, and with wavelength, how it is performing. And the definition is object exposed to an electromagnetic wave disperses incident energy in all directions. So this special distribution of energy is called scattering, and the object itself is often called a scatterer. So the energy scattered back to the source of the wave, called backscattering, constitutes the radar echo of the object. The intensity of the echo is described explicitly by the radar cross-section of the object, for which the abbreviation radar cross-section has been generally recognized. And also it is called echo area or effective area also sometimes. Some history for SAR. We are entering into SAR to understand what is SAR. So, conventional radar systems type were designed to achieve range resolution by the radiation of a short pulse and azimuth resolution by the radiation of a narrow beam. So, we are interested or we want to get two measurements, one range or along across track, that one azimuth resolution, that is the along track or parallel to the track, and one is range resolution, that is the across track resolution. These two measurements we want to, and this, why these two measurements, these two perpendicular measurements, suppose one two sides of a box, perpendicular sides of a box, because that we will further treat as a pixel, we will create image from that part only. This is also not important. So now we'll understand how actually SAR, why we, 1 second, suppose it is one sensor, this boy is one sensor, it hits this wall, it is our target wall, and it gets one signal, and second it transmits one signal here, and it reflects the signal this direction. So what happens, so basically this boy will go here and it will capture the signal, this reflected scattering. So what to understand from here, it is our flight, we are reflecting or transmitting the signal here, and it reflects the signal here, and we will capture, we will move from here this position to this position, and we will capture the reflected signal or received signal from here, from this position. In this same, suppose here the sensor first position, it reflects the object here, some object scatters some signal, and meanwhile it is going towards the azimuth direction or flight path, this way it reaches this way, this position, and it takes the reflected signal from here. Why this is important, this moving is important, why? Because from here to here it will measure, it will measure, okay, this is this much distance, this, and it is all is swath, because this much portion it will illuminate or it will hit the target, it is not in only one line. So it will hit this point also, it will hit this point also, and in between, this is called the total swath. And why this distance is important, we'll see that. This is some more geometry, this book, from this book you can refer, I don't think now you can understand. These are some of the terms. Incidence angle, what is incidence angle? It is not that, suppose it is reflecting, this is the nearby point of the swath, this is the far, that is the far range, near range and far range, these are the terms of radar and SAR. So it is reflecting, so this total portion is, it is hitting the target, sending the signal. So incidence angle is this portion, and this portion is, it is perpendicular to the earth. Okay, here it might not, imagine, but our earth is undulated, so the perpendicular line has, it is different to everywhere. So the angle is, the incidence angle it is measured from that perpendicular. This line perpendicular might be this way also. So it will, in that case, it will be that angle. So what range and azimuth that I mentioned many times, what it is called. So radar path or the flight, suppose it is moving this to this direction, and this is we called along track dimension or azimuth, and this is the across track dimension or the range. So we are interested to and suppose this is the swath, near range and far range, we will measure this way, we'll proceed this way, measure this way, and we want to measure this distance and here this distance also. But how we measure that we'll see. These are the what are the called the azimuth flight direction, the near range, far range, depression angle, that is the angle, the so real aperture radar, that is suppose we have not went or entered into the synthetic one, synthetic aperture, we are only seeing okay there is radar, it is moving and it is working somehow like that. So like this it is, suppose this way it is doing, I mean illuminating the surface and getting the signal. And it is, what are these lines, these are the, I mean ground to slant or slant to ground you can say. And pulse length and beam width, what is called beam width, what are the resolution cell, these things. So it is real aperture radar when we are using one real aperture or real antenna length. So how it works, it also I think you will not, I mean pulse to pixel, how image gets formed. First we get this intensity, then this we unwrap this phase total, it gets this, the wave we unwrap that total, then sampling, then we get some type of this intensity and power will come to that. Again some incidence angle, look angle, depression angle, these. This is again one visualization of the with the radar equation. Here the theta, the sine theta, this comes for the this incident angle, okay, for the slant range. So basically this is the azimuth resolution and this is the range resolution, that is the across. And why we are interested, because from ground to or slant to ground, slant range to ground range, we are interested. Now we'll see what actually synthetic aperture and these things are doing. The slant range resolution, that is the formula is the c tau by 2. That c is the speed of light, tau is the pulse this length and pulse duration by 2. So as I say, so range resolution, what it is, the across track, the towards the sensor is directing, across track resolution. And is it is easy to calculate, it is simple, the it is transmitting and it is receiving, so two times it is covering this length or this distance, so this distance by 2, so the pulse length or this the total this wavelength and into the light of speed, so it the total the distance it is covering going and coming back by 2, so it is the range resolution. Slant range or ground range, this depends on the incidence angle, and that incidence angle varies from sensor to sensor. And to calculate we need to consider the theta. This is the incidence angle. So to visualize slant range and ground range, slant range is this, and ground range is total. This it slant range is, I mean, it looks compressed, and when we that map that on ground or calculate with the angle, it gives us this type of flat proper image. Now comes the azimuth resolution. Why the synthetic aperture radar of SAR comes in scene? There we could work with the real aperture radar. Normally it is. Why to move that sensor? Okay, we can simply, how optical sensor works or other sensor works, we can mount somewhere and we can just map, detect, and get the signal and do the processing and get something. Why we move that? Why we move the sensor or the flight from one position to another and take continuous measurement? Because if I tell you with equation, so this is the equation. So beam width is equal to lambda by AL, that is the antenna length. So if we suppose, so beam width, we have to, we need that this beam width, this is called the beam width. So, and we are interested now in the azimuth direction, this one. So to increase the azimuth resolution, we can decrease this lambda. Okay, we have two options. Or increase antenna length. This is the azimuth resolution to increase this part along track, this direction, not this cross, along the path. So to increase beta from the equation, either we have to increase this wavelength or decrease this wavelength or increase this antenna length. So wavelength is fixed for sensors. We have to increase the antenna length. But how far can we increase the antenna length? That is the main thing where real aperture radar, it was not enough and we went for synthetic aperture radar. Because for real aperture radar, antenna length was suppose 100 meter, suppose. But we need, mathematically it is saying that we need 100 kilometers of antenna length. That is not, possible. So what we did, we synthetically increased the antenna length by moving the sensor. The basic concept of SAR is that we synthetically increased the antenna length by moving the sensor from one position to another, to azimuth direction, because range resolution, distance mapping is not any problem. It is just measuring the distance and that. But azimuth resolution, it had limitation, and this way we wanted to overcome this. Here how the synthetic aperture comes. So you can notice here these small parts. Okay, so these smalls are like, suppose one sensor. So previously what we were doing, we had to cross this 2 kilometer, we needed 2 kilometer long antenna. That is not real life, that is not possible. So we basically increase the antenna synthetically or artificially this much, from the here to here, moving from here to here. Okay, so moving everywhere and sending signal to here and receiving same time, similar time, just that simple concept. Sending from here, receiving from here, sending from here, receiving from here. Okay, and it works in microseconds and very high. That's why not that, I mean, the SARS sensors are very much costly, very high in maintenance. That's why the data are also very costly and not so much open source data are available. That's why only this is the reason so high power signal are, and other also the sensor everything are so heavy. So here this is the resolution of real aperture, this one, and resolution of synthetic aperture only this one, and we want the resolution smaller, in sense the numerical digit is smaller, so it is called the higher resolution. Okay, so numerically we need the smaller one. So for real aperture, what we were only able to this much was suppose illuminate this much and this, but to for high resolution or to cover more area, this is our solution. Also to understand beam width, I think to azimuth resolution the beam width to connect depends on the beam width and the slant distance of the antenna, because the beam, it is the beam and width it is called. So lesser the beam, more the resolution. More resolution in the sense numerically, it is lesser in number, lower in number. So suppose one beam width, it azimuth resolution was 5 meter. For smaller beam width, azimuth resolution becomes 3 meter. So it is more, I mean, acceptable for us, because then we call it higher in resolution. So that way, to increase or to decrease the beam width, we went to this equation. How it worked? To decrease the beam width, we have to increase the antenna length, and two, we are increasing the antenna length in synthetic aperture radar virtually. So some fundamental terminologies to know for radar or SAR is that energy reflected from the terrain to radar antenna is called radar return, and it gets affected by two types of properties. So you will, I mean, get in many books and many other lectures these terrain properties mainly, not the system properties. System properties are also very important. Okay, so I divided these two types. One is system property, that is the wavelength, their polarization and incidence angle, and another is terrain properties, that is very important, dielectric constant, surface roughness and feature orientation. That, so we will see which I mean, we can select, we can choose which wavelength to select, which wavelength sensor, which polarization to work with, which incidence angle is it okay to work with. Then we, the terrain properties, we will see which one we want to detect. Similarly, as I mentioned before also, not this detail, this radar finally wavelength and or radar bands. So these are the, one is missing also, Ka, K, Q, XC, SLP. So as we go down, the wavelength increases. So for L this, for P this. So radar return mainly depends on the wavelength or the frequency used. Terrain features have a unique interaction in a particular wavelength, and hence the return is also unique for the waveband used. Shorter wave bands have atmospheric effects because of the interaction with the atmospheric water vapor. Longer wave bands comparably penetrate through the skin of the Earth's surface. And the X band is not commercially. These are XK, KK, QX. These are normally accessed by the security military persons. X band we can purchase still, some are available. C band, the Sentinel 1 is available open source, one C band data, one sensor. S is coming now, the NISAR recent, that is the US and India collaboration, that sensor. There S band will be there, L band will be there, and L band allows two data we will work with, and P band another. P band also we are not allowed to use open source. So these different for different wavelength the same area looks like this. The X band VV polarization, it looks like this. C band, the wavelength increases this. Finally L band, you will see it looks this. So how detailed it is going, or detail it is mapping the area. So heavy rain in the lower center of the image. So here heavy rain occurred. So as a black cloud in X band image, because it could not penetrate. It rained this portion area. It was cloud there. So 3 centimeter could not penetrate the cloud. So it's showing a black patch. C band somehow penetrate, faint in C band. One depression we got. But invisible in L band, that is 23 centimeter. It totally penetrated all the clouds and vapor. So this portion here. So one thing to see, water is dark in all the three bands. Okay. Water body, you can see this river is flowing. Here also river is flowing. This water body is dark. Why in SAR image water body is dark? Because water, as we saw the scattering, so for microwave signal, when it gets the water surface, it gets reflected, or it happens specular reflection. So the reflected signal is away from the sensor. Okay, so it does not reach it goes to another direction. It does not come to sensor direction because the specular reflection happens. That's why there no energy, the radar will, the sensor will not get any energy. So there it appears dark, and where it gets energy, more intensity, there similarly it will get more brighter. That's why in SAR image, this water body looks, in SAR image water body looks darker, and in optical also it looks darker. Why? Both are different. In optical it gets absorbed by the water body. In SAR it is because of the specular reflection. So different bands has different also these applications. So radar wavelengths should be matched to the size of the surface feature that we wish to discriminate. This is very important. Often we skip. We want to in terms of shape and size, the wavelength can capture or sense that target only, which has similar nearby measurement or nearby this size of the target. So eyes discrimination, small features like very small particle using X band. Geology mapping, large features use L band. Foliage penetration better at lower frequency, use P band. So in general C band is a good compromise, it says. Somewhat an average result you will get with C band. that is Sentinel-1 data, and it is open source. So wavelength influence, again some pictures. X band, how it shows mixture of crops and woodlands, but in L band, I mean very higher compared to X band, very high in wavelength. So how it looks, I mean how the it actually target interacts. So basically what happens here, it is underneath there is water. Okay, so it is here, it is the reflected signal comes from the top of the surface, but here not, it penetrates to some centimeter level to the surface vegetation, and it gets the water beneath. That's why it also gets darker, the water. So it is it is very important to, I mean, not only identify, to get in, I mean that take into consider that band, that okay, this band it will look these things, this band it will look these things, it the both the thing both look the same, suppose sensor or not same sensor, both two sensors looking differently. Similar the how the C band, L band, P band, how it is looking to different. You can see the P band more detailed and more, I mean not that much bright, I mean that much bright, these are not that bright. So this is the, I mean, choice of radar wavelength. So high wavelength, more difficult in processing, need larger antennas, feed simple electronics. Low wavelength need more power, more difficult electronics. Now comes the polarization or bands. This is to understand that, I mean, one every signal we are sending, it can be of two type. So as we saw, we are sending these sinusoidal curves, but this in 3D space, this direction, I mean it is electromagnetic. So one is this perpendicular to y axis, another is perpendicular to this z axis. So it is sending two types of signal. This vertical, that is oscillating to the moving of the, suppose it is moving this way, the signal is moving y directional, perpendicular to the moving direction, that is the property of electromagnetic wave, and another is horizontal to the. So we will send and receive back the combination of these two types of polarization or bands. Here I will not, here it is called polarization, I will not use the term polarization, I will use the band. Why, I will tell after some time. So first this is very standard, VV, HH, VH, HV. To understand this, how we will understand or read this, it is sending the first term and receiving the second term. So V it is sending, V it is receiving, then one component it is VV, polarization. Then similarly for this, H sending, H receiving. But for this, it is sending V, receiving H for some targets. Sending H, receiving V. So these four combination will take into consider. But these will not call totally polarization, because I think that I will come later. This we will say band. Firstly, polarization, when we'll call this polarization, because when you are transmitting, suppose one this signal, only take this vertical polarization, you are transmitting one V, pure V. You will get not this pure V or not pure H. Suppose for this combination, when you will get this pure V, VV. When you will get pure H, H. But you will get so many signals or waves with that makes angle with each other. Okay. I if I like sending this V, transmitting this V, we will get this signal also that has some angular, this signal, some angle it creates. Okay, not, you will get the pure V also and you will get this H also, but this way another angular, so many lakhs of crores of these signals you will get that has some angle with this. So what to do with those? That is why we call it polarization. Polarization, when we only filter the V and the H, that is what polarization. To understand what is polarization or polarimetry, better say, to the study of the domain that works with, it is nothing but the filtering. That okay, I am sending V, I am getting so many angular waves, but I am interested or I am filtering out other any angular waves. I am only taking the V part only, the receiving V. That that is that has the filtering concept, nothing but a filters. That is why we, I mean, call it polarization, or the band, polarization band. So this is how the polarization term comes. It is not like bands or channels. We could call it band channels, but why we call it polarization? That is what polarization. So here the concept is near range, far range. You can see. So it radar, I mean, it needs some, so many SAR image needs pre-processing. I'll show next weeks, coming weeks in softwares, you can see. So many pre-processing, basic pre-processing steps for any, I mean, we have to get the image from raw signal to, I mean, we have to pre-process the signal or image before proceeding to any other type of processing as per our requirement. So for, I mean, those pre-processing, one steps these kind of distortions we tackle, this near range, far range. Okay, I'll show you this. This has some other thing, different flight orientation. It will look differently. The radar projection, how it looks in HV image and HH image. I wanted to show you the near range, far range. That image is not here. So near range, what happens? In far range, it gets elongated. I mean, near range, you can see how the more it goes this way, near to far, it gets elongated. Okay, it is not like it, because it is in angular direction. The measurements we can get from here, these are not the true. So how to correct those things? That is a problem. There are different examples. We have seen already the equations, the received power, transmitted power, what are the different parameters. So finally, we work with power, or we are interested in the received signal or received power, and with that we will measure the range and azimuth, resolution. So radar backscatter, what it is? It is the power received, that is equal to power per unit area target into effective scattering area of the target into spreading loss of radiated signal into effective receiving area of antenna. It is written from here. Okay, from this. So one thing is, first I will tell something power. What we from signal we get the amplitude. Simple, what we saw that one signal sinusoidal wave is like this. It goes like this. Suppose. So it has amplitude, it has phase. Okay, all this. So from amplitude, how to get this backscatter or this power, you can say. So that on, I mean, often we skip these details. To amplitude, I mean, it is simple, the simple equations. So amplitude, it is nothing but the intensity, it is nothing but the amplitude square or the power. Okay, intensity or power, that is square of amplitude, square of this. But the power we calculate for SAR, for radar, it is the log 10 based power. Power in dB, similar to the sound, decibel, sound unit. We calculate it in log 10. Why? These things, I mean, you will not find in any book, I think. So why we simply calculate all the calculations, so many things. It is power log 10 base, log 10 base. I mean, calculating that in dB. Why not to calculate or use that, direct that amplitude square, that power? Why to get the dB or log 10 based? Because when you do numerical, suppose you get the, you calculate um, the you get amplitude, you calculate the power, some numerical, some digits, it will be so, I mean, larger in value. Suppose 10 digits of one value. So what we do, for our handy, for our feasibility to work with, we get the log base, and log 10 based we get that log based. That's how it gets, I mean, into dB, into suppose how I mean, suppose log 10 base something. So we will get the 2 3 4 5 10, this type of digits, not 10 numbers of totally going on. So what is the conclusion? We get, or we measured in dB for our feasibility. It is difficult to work with 10 numbers or 20 numbers, so big digits. To work with 2 5 3 10, these things, it is very useful. That's why we take that in dB. These are very simple things, but better to understand in context of SAR. So now comes the radar backscatter coefficient, one terms. That is the main thing. That is the, I mean, this, after all this, from the starting, you will, when using any software or reading any this data, you will get this. So what is finally the radar backscatter coefficient? So we'll see that efficiency, the terrain to reflect the radar pulse, is termed as the radar cross section. So radar cross section per unit area is called the radar backscatter coefficient. It is computed as sigma is equal to sigma by A. So A is the area total. So sigma it is called, and sigma, not this one, that is measured in dB, that I said. log 10 based, that is the power, finally power. So the ground resolution is again depend on the slant range, distance of the target and pulse duration, which can be understood from the following equation. Nothing to understand. And reflection from different types of surface. Okay, these further next week lectures we will see different types of geometry properties, shape, size, these things. Now just to show you how different we have this type of different targets, different shape. One is this total smooth, another is this type of, another this can be. So we will take consider all of these things, all these type of targets, this also, this type. Corner reflector, this is these are the reflector, or these are the instruments, or we consider, suppose this type of things to calibrate the antenna. Okay, to get the actual value and for calibration, data calibration. There are different shapes and size. I think the ma'am must have covered already different types of reflectors, corner reflectors, trihedral, so many things. This type of that. So I think today and all most of the things today are taken from this book Skolnick, and I would suggest to understand SAR radar basics. This book looks very so much, but it is not. It is the Bible of SAR or radar to me, and you can refer. It is open source. In the PDF is available in Google. You can download and you can get all the equations for any numericals to understand, to read just as story. It is just one stop. And I think today I have covered the basics. So any question? Then I have prepared one setup, that is that how I teach, set of MCQ questions, and today the questions are very, it is when you will solve those questions or go through those questions, then only you, the our ideas get clear. So any question till now I want to ask? I will share the assignment. Assignment page or doc file I have shared, and I will share the anyone has any question you can ask. I will try to answer. You can message me or anything also, it's up to you. And if you are interested, you can answer. the questions and you can go through by yourself that. But today I would say the questions are very good and some questions I kept a bit tougher side to get you understand that okay, you will get the idea. Anyone has any question or anything you can ask, or you can also answer the assignment questions or send me the answers, anything. And also I every time I do this I am sharing my mail id because I work with this domain in this domain SAR and these things. If you have any question regarding processing theory, data, anything, you can mail me. I have shared my mail id. Any difficulty, any question or anything, mail me and I'll try to solve or reply those things. I have shared my mail id and I work on this domain, that's why I would love to help or I would love to share or discuss. Solving or answering the questions. One thing I would like to discuss is why, I mean, anyone, if one can answer that why our optical sensor, in our optical sensor, we look directly perpendicular to the below perpendicular. There is not side looking. Why in SAR we look, I mean, we take the signal or take send a signal by side looking? If anyone can answer this, these are the very basic questions and it should come into our mind and we should know. No one is going to ask us what is the range resolution, what is the incidence angle, what are these, but these things we have to understand, we should know. For optical sensor we just look directly beneath our the target, but for SAR sensor we look side by, we never look the below perpendicular. Try to find that answer, or better to try to think that answer by yourself. Finding anything will get, but why we are doing that for SAR, for radar? We could have just, why to look this side and do all those things, slant range, ground range, so many things, why to do those things? You can think about those. And for, you don't have any queries, I think. Any queries you can ask, message or any directly, and you can go through the assignments. It will just, and today's class is very important because it is the basics. You will not understand the further processing and hands on those exercise, hands on those programming, all those things, unless you understand the basics of SAR, how it works, what is all, what are the terms, basics. I think no one is interested. You can simply tell me the answers. That is how I like to finish my class. It is kind of revision. If you don't have any question, then I will ask. That's the thing. Or you try to solve by yourself and send me the answer. It is not like I will see later and I will, nothing is later. So I think today I have shared the assignment. You try to solve, and if anyone has any question or particular regarding any slides also, regarding any slides, and these all the lectures you will get in YouTube. Every week after the lecture you will get on YouTube channel. So anyone has any question, I am bound to ask everyone. Okay, so I think no one has any doubt, and so I am ending today's lecture. You try to, if you are interested, you can send me the answers of the assignment. You can mail me on my mail ID, and that's it for today's class. Okay, thank you.